The final concept that we have to learn about is rotational kinetic energy in this topic. And to understand why a rotating object has kinetic energy, we can remind ourselves that energy is the ability to do work. A rotating wheel can do work, it can push things and make them move, or it can produce heat. So we say that it has some energy. And to recognize that that's kinetic energy, if you think about a rotating wheel, all the little bits of mass inside the wheel are moving, and so all the little bits of mass have kinetic energy, and all of that energy combined is the rotational kinetic energy of that rotating object. So in this case, if we've wrapped a weight around an axle and we let it fall, as we have done in many of the experiments we've done in class, then as the weight falls, it will lose gravitational potential energy. The energy that it loses is turned into a combination of its own kinetic energy, because it'll have some speed, but it won't fall as quickly as it would if it were just falling freely. The rest of the gravitational potential energy is turned into rotational kinetic energy of the wheel. So there'll be like rotational kinetic energy like this, and this one will gain kinetic energy. Oops. So total energy is always constant or conserved. So we can say here, sum is turned into kinetic energy of falling mass, and sum is turned into rotational kinetic energy of spinning wheel. So the rotational kinetic energy equation, so remember that kinetic energy from year 12 is half mv squared. The equation for rotational kinetic energy, well, we've learned that for rotation m is I is rotational inertia, so we can say it's half I omega squared, which is in fact the equation for rotational kinetic energy. Here's a quick demonstration that that's the case for a spinning ring. So the kinetic energy of all the little bits of mass in this ring is half mv squared, but v, remember, is r omega. So the kinetic energy is half mr omega squared. So the rotational kinetic energy here is half mr omega squared, half mr squared omega squared, and mr squared is the rotational inertia of the ring. So we get half I omega squared. You don't need to be able to show this, but it kind of does provide a quite simple demonstration of the fact that these two things are the same for a ring. So if we look now at the student spinning on the chair, we have said that when she pulls her arms in, angular momentum is conserved because there are no outside torques. However, rotational kinetic energy is not conserved, it increases. So if we look at this equation, if I is halved, we've said omega will double. And what does this do to the rotational kinetic energy? Well, initially, if we say that the rotational kinetic energy is equal to half times I times omega squared, well, finally, we have RKE is equal to a half times, well, I is halved, so it's I over 2, and omega has doubled, so that's 2 omega squared. And if we expand out all the brackets and simplify here, we get a half times I over 2 times, well, 2 squared is 4, so that's 4 omega squared. So we divide by 2 and multiply by 4, that just cancels out. So that's equal to I omega squared. So we can see that the final one, the initial one was half I omega squared, but the final rotational kinetic energy was I omega squared. So so the rotational kinetic energy has doubled. And the reason where that energy came from is from the work that the person did in pulling the mass closer to their body. So it actually took work to pull those in. You had to apply a force. And those of you that actually tried this experiment, you would have noticed that pulling the masses in towards you actually required you to apply a force. So that work that you do adds energy to the system, and that's why the rotational kinetic energy increases. Okay, so let's look at how we can apply this concept of rotational kinetic energy. Consider that example of a weight on a string. So we can write an equation for the energy change in terms of m, I, h, v, and omega. So the weight starts off with, with an initial energy of mg h. H is the distance that it's going to fall. So h is this distance here. And that, so EI must be equal to EF. And EI is just mgh. That's the energy that the system starts with. So nothing's moving to begin with. The only energy that's there is the gravitational potential energy of the dangling mass. So when it's allowed to fall, that's going to get converted into two things. A half mv squared of the little mass plus a half I omega squared, which is the rotational kinetic energy of the wheel. So basically what we've done is GPE of the mass has been converted to KE of the mass plus KE of the wheel. Okay, this is a challenging extension task. I'm going to leave that for you to have a go at as a challenge. Why is the acceleration of the falling weight not 9.81 meters per second squared? We've answered this before in terms of the forces acting. We can answer it now in terms of the energy as well. But the simplest explanation is that there is a tension force slowing it down. And we can also say in terms of energy, sum of its GPE is converted to RKE of the wheel. Consider the turntable drop example. So that's the experiment that we did in class where we dropped the ring on top of the spinning turntable. Is that an elastic collision? Explain. Well, an elastic collision is where the kinetic energy is the same before and after. So this is definitely not. No. And the reason it isn't, the reason we know that it isn't, was that there was friction between the turntable and the ring. And that friction must have produced some heat. So that means that EK initial is not equal to EK final, which is the condition for an elastic collision. Okay, we can't really do this demonstration at the moment, but we can still do it as a little thought experiment. So if we have a cart that races a wheel down a slope, we can predict which will win using energy. So the cart will win. The reason the cart will win is that it has only its tiny little wheels that are going to be spinning. So we can say more of its gravitational potential energy will become translational kinetic energy. Whereas for the wheel, much more of its gravitational potential energy will become rotational kinetic energy. And the rotational kinetic energy doesn't contribute to the forwards motion, because when something rotates, there's just as much moving backwards as there is moving forwards, so it's not going to cause the wheel to move forwards any faster. So this is a question that's going to allow us to apply a few of the different concepts we've used. So Hannah slows the spinning turntable by holding her finger against the edge. We're given a radius here. Maybe make a note that that's 0.20 meters. And a tangential force, so that's 2 newtons. It goes from 5 radians per second to 0 in 10 seconds. What is the rotational inertia? So we have enough to work out tau here, the torque. And I think we have enough here to find alpha. So we note that I is equal to tau divided by alpha. And this is all the experiments that we did in class involved these three as well. So that where we worked out the rotational inertia of the different wheels. So in this case, tau is equal to, the force is 2 newtons. It's force times radius, which is 2 times 0.2, which is 0.4 Newton meters. And alpha we can figure out as well, because we know how much the speed changed and how long it took. So we know that alpha is equal to delta omega over delta t, which is final minus initial, so 0 minus 5 over 10, which is 0.5. It's actually negative 0.5. That just indicates direction, and actually the torque is being applied in the same direction that it's accelerating, so they're both technically negative. And rotational inertia is always positive, so if you were to end up with a negative answer, then you kind of know that it should have been the other way around. So this is in radians per second squared, and then we note that I is equal to tau over alpha, which is 0.4 over 0.5, which is 0.8 kilogram meters squared. Okay, next we're asked to find the turntable's mass, and we're told that it's a solid disk. We now know I, and we know R here. So I is equal to half mr squared for a solid disk. So m is going to be equal to 2I over r squared, which is 2 times 0.8 divided by 0.2 squared, which is 2 times 0.8 divided by 0.2 squared equals 40. kilograms. That's a seriously heavy turntable. Okay, so just to summarize then this last section, the angular momentum is L equals I omega for a rotating object, or if it's just a single point mass, we derive this equation as m times v times r, where v is the translational speed of the object that's moving in a circle. Rotational kinetic energy is half times I times omega squared, and rotational kinetic energy is usually not conserved. We usually lose some to heat. Okay, so that's the end of the rotation topic. You should be able to use the concepts from this topic to answer all of the questions in assignment 4. There is a one of these fill-out grids which will allow you to kind of master the use of the various equations, and I do recommend you have a go at that. I'll provide some answers for that as well.